All right, let's have a look at this a different way now. We just talked about how Pascal's triangle might be able to help us with this. And another thing that we've talked about before and learned before in class is what's called the binomial theorem. When we took the binomial theorem way back in Unit 2, I believe it was, and we expanded binomials like this one, p plus q to the n, we knew we had a pattern that we could use to actually generate that answer when we multiplied them out. A new definition for you, because these are brand new letters that we're starting out with that we have not defined yet. From now on, P will be the probability of success. Remember we talked about Bernoulli trials being success or failure. Well, P is going to represent that probability of success. And Q, from now on, will be the probability of failure. N represents the number of trials. And in this case, we are flipping a coin 3 times, so n equals 3. And what we need to do then is use the binomial theorem to expand our P plus Q, which is success plus failure, raised to the n. Well, here's what it's going to look like, and this is the most simple way to explain it. If we have flipped 0 heads, well, I want you to think about what that really means. 0 heads means that out of 3 possible flips, we got 0 correct. How many pathways on that tree diagram had 0 correct out of 3 flips? Well, 3 choose 0 is 1. And one way would be tail, tail, tail. That's our tail, tail, tail method, right? Which is number of heads is 0. So 3 choose 0 represents out of 3 flips, we got none correct. Times the probability of success, which we all know is 1/2. Success, P, is 1/2. How many times did we get success here? That means we flipped ahead. Didn't get it at all. So 0 times, 1/2 raised to the 0. Times the probability of failure, that's also 1/2. That means I must have flipped a tail. Well, if we didn't get any heads, how many tails did we get? That's right, we got 3 tails. Okay, this looks just like one of the terms we would have gotten from the binomial theorem. If you actually multiply this out, we get 3 choose 0, which is 1, times 1/2 to the 0, which is 1, times 1/2 cubed, which is 1 and 8. What's 1 times 1 times 1 and 8 equal? 1 and 8. That's exactly the same answer as we had in our probability chart, or from the table, or from the tree diagram for that matter. Let's go to 1. If we got 1 head, one successful thing, which was flipping ahead, that means that out of 3 flips, 1 of them was successful. How many pathways on that tree diagram are there for 1 successful head? Well, we counted them. There were 3 of them. 3 choose 1 is 3 ways. Times 1/2 to the 1 times 1/2 to the 2. We must have gotten 1 success. We also must have gotten 2 failures. It doesn't matter the order we got those in. It could have been head, tail, tail, or tail, head, tail, or tail, tail, head. But regardless, we got 1 head and 2 tails. And if we figure this out, 3 choose 1 is 3. 1/2 to the 1 is 1/2. And 1/2 squared is 1/4. 3 times 1/4 times 1/2, that's 2 times 4 is 8, is 3 and 8. That's exactly what we got in our table. Interesting. Okay, let's do 2 more. 3 choose 2. Now you get the hang of this. 3 choose 2 times 1/2 to the what? Well, we must have gotten 2 heads here, 2 successes, so 1/2 to the 2. Failure must have happened once, and this is 3 choose 2, which is 3, times 1/4 times 1/2, which is 3 and 8. One last one. You can see how this is actually quite easy knowing and understanding the binomial theorem, because we're just doing that same thing here. 2 2 plus 1 is 3, 2 plus 1 is 3, 3 plus 0 is 3. All of this relates back to that binomial theorem. Okay, this is all 3 heads. So 3 choose 3. Out of 3 flips, or 3 trials, 3 of them were successful. 1/2 raised to the 3, 1/2 raised to the 0. 3 choose 3 is 1. 1/2 cubed is 1/8. And 1/2 to the 0 is 1. That is 1/8. Well, look at that. We've got the exact same answers as we would have gotten using the tree diagram. So this is a very powerful method for calculating these probabilities quickly and easily. Only for things that involve Bernoulli trials, though. All right, let's go through this one real quick then. In example number 2, we have a coin that's not fair. Not fair meaning it's not half and half. The probability of tossing a head is actually 60%, so there's a higher chance of tossing a head. What is the distribution for the number of tails, it says, if the coin is tossed 4 times? Okay, well, I'm going to do the first few with you at least, and then I'll let you do the rest to finish this table off. How many tails could we get in 4 flips? Well, we could get 0 tails, we could get 1, 2, 3, or all 4 tails. That's what's possible here. But what's the probability of getting 0 tails? Think about what that means. If you got 0 tails, it means you must have flipped 4 heads. 4 heads means this. In 4 trials, we're going to use the same idea using the binomial theorem, but now it's 4 trials. Out of 4 trials, we got 0 successful things happening. What's a successful thing? We're looking for tails, not heads, right? So out of 4 flips, we got 0 tails. What's the probability of getting a tail? Well, it's not 1/2, it's 0.4. It must be the opposite of 0.6. And that happens 0 times. How many failures did we get then? Failure in this case means we flipped a head. Failure happened 4 times, and you can calculate that. I'll do it quickly right now. 0.6 raised to the 4 is 0.1296. That's a 12.96% chance of flipping 0 tails. Let's do one more. This would be, let's see if you can figure this out. The combination for Pascal's triangle in the 4th row is 4 choose 1, which also means in 4 trials, 1 thing came up, 1 successful thing, or 1 tail came up. Times 0.4 represents the chance of success, that's P, and that happened once. Q is failure, that's 0.6, that's the probability of getting ahead, and that happened 3 times. 3 plus 1 adds up to our 4 trials, and we can figure this out. 4 times 0.4 times 0.6 raised to the 3 is 0.3456. I am going to leave it up to you to finish off 2, 3, and 4 following this pattern. It's not a very difficult pattern to follow, but you need to now understand how to apply the binomial theorem to represent these binomial distributions.